Hi all who's joining. We are pretty much ready to start. Let's wait for others to join. Hopefully we'll start in a few minutes. Feel free, grab some beer, snacks, and we'll be starting soon. Hey guys, one more time. We are waiting others to join, probably one more minute, and we will be starting our webinar presentation about databases on Kubernetes fundamentals. Bear with us. Till we are waiting for additional one more minute, please join our Slido channel. Look through the GitHub repositories and probably join into our Slack community. You can find all the links on the presentation. You should see it on the screen. Yep, we'll start in 1 minute. Okay, so let's get started. Hopefully everyone can hear me, see me well, and can hear a presentation, see presentation, and everything is good and smooth. So good day, everyone. My name is Alex, and welcome to our amazing stuff spring meetup session. It's supposed to be a series of meetups consisting of a sequence of 3 meetups. Hopefully next time we'll be able to meet in person, have a standard chatting and beer part. By the way, that I hope that you got all hands on our amazing stuff swag boxes and enjoying good quality beers and snacks. So let's grab some beer, let's grab some snacks and get started. As I mentioned before, our plan is to have a series of topics around the databases on the Kubernetes and how it can be beneficial from a business and technical standpoints, as well as how to build it, maintain, and secure it. So please, as I said, check out our Git repository. It has some examples for this particular webinar. Feel free to track our Slack channel and community, and please ask any questions through the Slido portal so we can answer them through the presentation. So today we are going to talk about the fundamentals, and let me introduce you agenda for today. We shortly go through the introduction session about why we actually do need databases on Kubernetes cluster. Later, we'll move to some hardcore part about examples around the block storage options and cross-region mobility. And after all the stuff, you'll have option to ask questions through the Slido channel. So let's get started. So our first speaker, it's actually me. I'm pleased to introduce myself and switch a role to the presenter one. So good day, everyone. My name is Alex, and I'm system owner in Foundation Services team at Mambu. So as of a background, I've started my career as a database engineer somewhere like 10 years ago in large enterprise, solving all kind of issues with on-prem database clusters, backup, DRs, and it was a hell of a job, to be honest. Then the cloud appeared, and as a member of infrastructure team, I was eager to move everything to the cloud. Give it all was our intention. Do not bother about updates, tooling, and other operational stack. But why then we need a database engineer at all? So that's how we came up with this new actual trending stuff. Something to justify existence of the database engineering. Yeah, don't worry. It's actually a joke, or it's not. So why do we actually need all the database on the Kubernetes cluster? So how we joined an evil side if we're supposed to actually fight it in the first place? We found out actually that when you are going into the multi-cloud environment and trying to do some multi-cloud stuff, it appears that different cloud providers supports basically different services and functionality. Like MySQL in AWS is not actually same as a MySQL in GCP or Azure. As an example, you probably know, like in AWS, you have IAM policies. In Azure, it has AD, and probably nothing is in GCP to address that matter. Another point is that basically why one looks into the multi-cloud world is to avoid vendor locking. This issue can be addressed by migrating some data from one cloud into another cloud vendor. And you should do that easily if that's required, because not all the clouds are fully reliable in particular regions. Also, as any startup, we would like to be on the bleeding edge of technology, which means we want all the new technologies right now and out of the box. So try to find any cockroach DB in any cloud provider as a service, or for example, MongoDB. Currently, it's not totally available in there. Let me switch. Okay, so what we actually do right now. So currently we have old school databases like Postgres, MySQL, which are actually not designed to be run in Kubernetes. It lacks a lot of tooling. It has a poor support from a Kubernetes point of view. It has a really small community who run it on Kubernetes. You can ask why. I can't answer this question, but currently this is a situation. All modern DBs, which we're kind of looking into, like Cockroach DB, Vitess, TIDB, and others, they are built with thinking about the Kubernetes, like operators in mind. It looks pretty cool. It tries to imitate API similar to the PostgreSQL or MySQL, but not actually fully compatible with old school databases. So migration is a kind of a hell. And as anyone, we have some challenges in that space. So modern databases, it's really hard to maintain. Lots of different DB clusters in it. It's really hard to automate and look after them, upgrade and other stuff. It's much easier to do in one large, huge cluster and split it between different environments and different tenants. Additionally, from our tests, Kubernetes storage layer looks stable, but with some challenges, primarily on the performance-wise nature. Like performance, for example, CSI plugin can provide a unified way across any cloud providers, but it sets additionally performance issue. So performance as a storage in different cloud vendors is actually a different thing. That's what another presenter today will be talking about. So all the tooling around these storage layers, all the complexity, it adds to the support penalties for the Kubernetes storage layer. Another part is that the different features for the storage layer in different clouds. So you need to manage that one. At least there are good points about it that sometimes, usually encryption and backups are supported out of the box, so nothing needs to be done there. So yeah, that's where we are, and that's what our state is. We have definitely some challenges in that world, and we will be solving them and moving forward with our solution. So thank you, and let's move to the question. So please join the Slido. Let's see them and let's try to answer them. Gedre, could you do a support for me and share the Slido channel? Okay, so I would say the worst challenge right now is to spin up all the supporting toolkit for databases on the Kubernetes cluster, because when you use the database as a service, it's pretty simple to use it out of the box, because backups, migrations, updates is all done inside the service itself. So basically, that's why we actually buying the service on the cloud provider. And when you try to implement that yourself, you actually need to implement all this toolkit into your current service providing. So all the operational part is basically on your side. So that's probably the first and the most challenging part of it. Why not ELK or Kafka? So to be honest, it's slightly a different nature. So yes, you can use these both technologies right now, but it's not purely a database engine, which we kind of treat it to be in most of words talking about the relational databases. So we definitely are doing ELK clusters and Kafka on top of the Kubernetes, but that's basically a different nature of things. So yeah. If I answered that well. Which of the database services you think are the most ready? To be honest, we have lots of challenges and all the work currently is in progress to spin up the database on the Kubernetes. I would say that when I talked, I mostly mentioned that the modern database like CockroachDB, for example, or Vitess are mostly ready for the use of the Kubernetes one. We are currently in progress of testing this out in full nature and full scale. However, we will be doing it all for any other products we are currently using inside our infrastructure. But I would say that's the newest one are the easiest one to run on Kubernetes. Okay, cool. Have you already found a decent solution for this problem? Sorry, Benes, probably I'm not pretty much sure about which particular problem you you asking. If you could reclarify your question slightly. Okay, is industry going back the cycles again? Unmanaged, managed, unmanaged. We call it the nature of cycling around the world and infrastructure. So that's basically true. But in each step, when we're cycling back and forth, we are actually inventing something new. So something more efficient, more scalable, and else. Okay, so let's get to another question. In my opinion, RDBMS are not supposed to run in Kubernetes by design. Change my mind. That's a good question. That's a really good question because stateful databases like RDBMS are not really ready to do that one. As I mentioned, we have tested out this old stuff for the PostgreSQL and MySQL, but you usually can't do that one in Kubernetes cluster. Why is that? It's because you can invent a specific layer, like for example, storage one, which will abstract out a lot of complexities by use of the databases in the world. So that's what the next presenter would be talking about. So bear with us. We probably can change your mind by the end of this presentation. So biggest problems while trying to run high-loaded databases, 100K plus IOPS, many GBs. Probably I will leave this question to be answered by next presentations because it's slightly out of the future. I think it would be addressed later. So let's leave it for now. Okay. We have some time for more questions if you have. I think 1 or 2 minutes. Okay, Benes, as a problem, I was thinking about having a production-ready database in Kubernetes that is as easy to set up and operate as platform as service offering. To be honest, with a kind of part of experience from old legacy world in kind of enterprise supported by yourself on-prem database solution, it's possible. So this problem can be solved, and there are lots of tooling around to support database in production ready cases. And it actually was done previously in a lot of companies. Yes, it has additional penalty of you need to have a specific organization inside your company to support and operate all of that, but it's, to be honest, doable. By all database, you mean relational one, row-based database management systems. By all database, I mean the ones which were designed to work on a kind of computed node way, which is one server database and can be shared between different servers through the partitioning and sharing options. I mean that by one, old ones, so like MySQL, old, not old, but current versions, PostgreSQL or Oracle databases, these ones probably. Okay, think that's these ones are answered. Great, let me get back to the presentation. Okay, so we move through the questions and welcome to our next part, and please welcome Augustinas Tirbis. He will be talking about storage for your database and Kubernetes. Augustinas is a director of engineering and Cast AI. He worked a lot with the different virtualization and storage solution in different parts of the world, like starting from the Lithuania, ending up in Singapore. And he likes biking, reading books, and all other cool stuff. Augustinas, please welcome. You probably is on mute, sorry. Please unmute yourself.
Mute. Hello, hello, can you hear me now?
Yeah, we can hear you, cool.
Great, so thank you, Alexei, for announcement and kind of shared why I kind of know a few more things about Kubernetes. So I worked 15 years ago as a database administrator as well, and currently at Cast, we're basically saying that Kubernetes is the cure to multi-cloud vendor lock-in and cost optimization. So we think that Kubernetes solves a lot of problems, and I want to show what's happening inside Kubernetes when you try to plug storage to your database or any stateful applications. And I'll let you decide if it's ready or not, but I'll show what's under the hood. Right, so Alex explained about all types of databases. So do databases in modern times in 2021 do still need storage? And by some saying if database cannot retrieve data, it's not really a database. So you have to have some persistence layer to write so you could read data, right? So let's agree that all databases need storage layer. So three types of databases, not to repeat what Alexei said. So MySQL, Postgres, MS SQL. So from storage point of view, they were designed with the mind that there's a storage assigned to this database, and the storage is highly reliable. That, yeah, it basically expensive storage, and usually in these databases, you have single copy of data, and if that data kind of goes down, your database is kaput. So you need really expensive storage, and that storage usually is by performance-wise tailored for random input-output, because when you write something, insert information, you need to split pages and etc. So a lot of random stuff happening inside. So as Alexei said, they were not really tailored for public cloud and Kubernetes. Second group of databases, modern databases. So Cassandra, Elastic, Yugabyte, Cockroach. these databases, usually you would have like 3 copies of same data. You would have at least 3 servers hosting 3 copies of data. And if one of the copies would die, it's not really a big problem, right? You still have a bunch of copies of your data and they can replicate and recover, etc. So these distributed databases, they don't care about storage reliability. Only thing they care is for throughput, raw throughput. And usually like Cassandra database is used just to quickly dump a lot of data to it and read it maybe later, but a lot of throughput is a priority. And lastly, just to mention, in-memory databases, so most notably like a Redis persistent database, it does require storage, and it's kind of somewhere between those two. It's just there, and it's quite popular on Kubernetes. Right. So as a side note, many years ago, I bought 1 Bitcoin for $50. That was many years ago, and it was quite an investment for me. Return on investment. So last year, I read this book, Designing Data-Intensive Applications. That book costs about $50 as well. And I believe it's bringing me same return on investment as that Bitcoin many years ago. So if you really want to understand how databases work, I cannot recommend well enough this book to help you understand. Okay, so that was a short reminder about current state of databases, and just quickly answer about which database, to extend Alexei's answer, which database is most ready for Kubernetes. I spent quite a lot of testing with Yugabyte, and I believe that probably is the one which kind of provides relational database logic, but is actually modern database. So, all right, so storage. And so if you go to most popular public cloud like AWS, you would see 3 types of storage on any cloud actually, but let's go with AWS, it's most known one. So first storage type, it's file-based storage. It's usually used for in form of a file server where you place and read files, share files with your colleagues, and etc. And file system storage is not really tailored for databases. So let's put it aside. Second type of object is object storage. And object storage is quite similar to file system storage. The only reason why object storage was invented, if you, for instance, you want to store a few million of pictures in one folder, most of file system kind of break down. So object storage doesn't have file system, but it works kind of like file sharing platform, right? And lastly, main dish for my speech is block storage, and on AWS it's called Elastic Block Storage, and it has a lot of options, etc. And as I mentioned, on every cloud you go, like on Google it's called persistent storage, on Azure it's called Azure Disk, and whatever. So it's available anywhere. So block storage usually comes in 2 flavors. So one flavor is local disks. So you have a disk, you insert the server, and your server has local disk. That disk is inside the server. It's usually attached through SATA, Is or NVMe interface. It kind of defines the speed, how your server can interact with the disk, and each disk have its own interface. So you can have a lot of throughput from those local disks. And as I mentioned, so if you want to run like Yugabyte, Cockroach, Cassandra, Elasticsearch, that's where you should be aiming for. Local, high-performing storage. And if you go to any cloud provider, there are quite a few VM types which provide local storage. Basically, pick CPU, RAM, and based on VM size in a family, you get more and more storage. So there are many options tailored for that. Okay, second type of block storage is the remote storage, where storage is not on physical server, it's somewhere behind in some storage backend where you reach it through the network. And many servers can write and read from one storage backend. So in private data centers, fiber channel is the king. I would say it's probably most it's a storage solution for grown-ups. If I would say that most of critical information in private data centers are being hosted on fiber channel storage arrays, and they are very reliable, they're quite fast, and they are ridiculously expensive and complex to manage. So that's why many companies in private data centers have storage administrators to do that. And because of the costs of fiber channel infrastructure, there's none of it in public cloud, because public cloud is all about price and speed and etc. So on public clouds, and it's also becoming quite popular in private data centers, you swap fiber channel network for just a regular network switch, and you route your storage through basic network with the network card and etc. So most popular protocol is Is Csi for that. And for instance, if you go to DigitalOcean, all storage is transported through Is Csi protocol. But biggest cloud providers, I would say, are using software-defined storage proprietary solutions. There are quite a few of those. And Thomas, after my demo, will actually demonstrate one software-defined solution, Portworx, and what kind of brings it to the mix. Right, so that was a basic refresher on storage. So last slide before jumping into Kubernetes. So if you have database like MySQL on a physical server installed, and you need storage for it, what things you need to do to bring storage to that database? So first, you need to understand what kind of storage you want to do. Mainly, how big is the disk? How many IOPS that disk needs to handle, or volume, and what's the throughput requirements. Second is somebody needs to actually create this volume, either your storage administrator, or if there's like self-service portal that you could do on your own. Third step is that volume needs to be added to the server. It can be like local disk, or it can be or number of different types of local disks, or it can be remote storage, and usually in public cloud, it's a remote storage. So you basically mount, zone, and mask that volume to the server, so that the server could see that remote volume. When you see volume in the server, you need to create a partition. When you create a partition, you need to format it with some choice of file system. When you have file system, you need to mount it to a particular directory. And then last kind of thing is you tell your database engine to drop data files to that directory. And that's it, profit. You have a database which can write and read data from persistent storage. Great. So Kubernetes. Some people think that Kubernetes and containers solve all the problems. Actually, it doesn't solve like world hunger, disease, and war. So where do Kubernetes come in? I like an analogy thinking about Kubernetes as a event organizer. So if you're a small shop, have a few servers, or analogy, you're meeting with few friends in a local pub, you don't really need that event organizer. But if you are responsible to host like 100+ people company Christmas party, you need some professional help, event organizer, in this case Kubernetes, because it brings new sets of challenges that you're just not facing when you are running in a very small shop, when you have like 1, 2, 5 servers, right? So in Kubernetes, same thing for attaching storage to your database would look like. First step is the same. You still need to understand your application patterns, how much your data you're going to have, how fast you're going to read and write, and what's the network throughput for that. And all that boring technical stuff is actually covered for you, and you don't have to do it because it doesn't add value. It's all technical steps that can be automated, and Kubernetes as a solution solves that already. So only last part 7, you need to just specify a directory where the volume needs to be mounted, and that's it. You have a working database. So to help understand how Kubernetes does all these steps that are kind of put away that are handled automatically. I have an analogy that provisioning storage in Kubernetes is like renting a car. So imagine soon you're flying to France and you want to rent a car to travel around there to have fun post-COVID vacation finally. So before going on a plane, you would want to order the car. And first thing, you have a checklist. You want to specify minimum set of requirements for the car you want to rent. Like if you have 5 family members, the car needs to have at least 5 car seats, right? Second is you pick car class. And it can be like economy class, luxury class, based on your budget. You want to have more horsepower, less, etc. It's all depending on your preferences and budget. Then next step is concierge. So when you land in Paris in airport, you expect that the car will be actually somewhere near airport and somebody will give you the keys to the car. And when you sit in a car, that car is actually clean and it has a full tank of fuel. And that's it. You have a car, let your holidays begin. So let's jump into more technical explanation of this analogy. So you as application owner need to specify your minimum set of criteria for your storage, how much you need of it. Like car seats, like I can say like 500 gigabytes. So some of you might be thinking, if I have 5 family members and I'm flying to Paris, wouldn't it be great just to drop off your kids at the airport and take 2-seater sports car? Wouldn't it be better holiday? But if somebody more responsible adult is actually doing your storage database, they will be choosing more wisely. So persistent volume claim, this PVC, is a Kubernetes object which kind of allows you as application owner specify what you want to from Kubernetes. So you need to create one persistent volume claim for one volume because they have one-to-one mapping. So, and you have to specify 2 things basically. So one is you have to specify name. It's usually how you're gonna identify that it belongs to a particular application, like payroll or whatever. Second is you have to specify how big is the storage, how big is the volume size you expect your database will write to. And that's basically it. This is the minimum thing that you need to do as an application owner by not being Kubernetes administrator. So there's also an option in the middle storage class. And sometimes in Kubernetes, storage class is already pre-created as default, so you don't have to actually pick it. But a storage class, think about like a car class. Is it luxury and or fast or etc.? So car, for instance, public cloud can define storage class in public cloud can define, is it like slow spinning disk or SSD or very fast SSD disks. So these are things are defined by storage class. So storage class usually are pre-created by Kubernetes administrators, and you would usually have 2, 3, maybe 5 in form like you have a bronze, like budget, slow storage, then silver, gold, platinum, and whatever. So, and if you're gonna have hundreds and thousands PVCs in a cluster for every disk, you're gonna have just few storage classes. And as a user, you just pick one and you don't have much flexibility to do anything about it. It's your Kubernetes administrator. But as this session is about shedding light what's under the hood, so I have an open storage class Kubernetes object, which basically shows what it is. So we have a name, silver, and then provisioner is it's AWS Elastic Block Storage, the storage backend, and few parameters that would help understand Kubernetes, what kind of storage is silver. So GP2 volume type and file system like ext4. So I made a screenshot. So today in AWS EBS service, you can create 7 types of volume, and they differ by speed, redundancy, and performance. and also you can specify file type. So you expect your Kubernetes administrator to just kind of pick 2 or 3 and that's it, but you can tailor it if you want it, right? So there's a lot of flexibility to prepare this environment for application owners. So you might be thinking, okay, why just not pick best of the breed and just use it? Why do you need bronze and silver? So here are prices for storage. And you can see the prices even on same cloud for different tier of EBS or Azure Disk can differ widely several times. And costs in the cloud is one of the biggest nightmares that today companies are facing. So basically, if you're a Kubernetes administrator want to create default storage class, it should be probably more on affordable end. Right. So we talked about PVC. So one PVC for each disk. Then in each PVC, you define storage class, kind of gold, silver, or bronze. Then there are quite a few options, advanced options for storage class that are still available and kind of essential to understand before going deeper. So I marked a few options in a storage class. So storage class can be default one. Let's skip a bit provisioner. Reclaim policy means when you're gonna delete your, for instance, MySQL database and PVC belonging to that database, what Kubernetes should do. So for instance, in development environment, you would want to delete data because it's development stuff, right? You don't want to pay for storage which is not attached to any application because you have to pay for that storage. Or for production, you can leave it retained just in case your backups doesn't work like your expectation. So last option is volume binding mode. So Kubernetes could create volume as soon as you create PVC volume claim. So, and it would create in a random availability zone, and then you're gonna attach your database to it. So it means on every cloud, in every region, there's at least 3 availability zones. So availability zone is like physical data center. In each availability zone, there's a separate storage and servers. And you cannot mount storage from one availability zone to the server on other server, on other availability zone server. So they need to be in the same data center. So if you specify to create storage in particular availability zone, you are not allowing Kubernetes to do its magic, be that event organizer. So if volume binding mode is immediate, you are acting as a crazy bride who's in her wedding does micromanagement, right? You have to let it go. You have to let Kubernetes decide where it wants to place your, for instance, MySQL or Cassandra pod container. And Kubernetes will look like resource utilization in different availability zones. It can decide based on your application high availability distribution requirements. It's going to do pretty decent logical placement where your database should be running in which availability zone. And if you have setting wait for first consumer, it means only then storage will be created and you don't have to micromanage all this. Storage basically will follow your workload. And these are basic or advanced storage class options that kind of important if you're administrator to really understand what's happening and how safe is your data and why maybe some containers don't see their storage. So let's jump to provisioner, what it is and what is CSI Driver. So CSI Driver is like this concierge, which will kind of go to car garage and bring the car to you, give you keys, and the car will be clean and with a full tank. So CSI Driver is that technically just a specification. And this specification basically says for every storage vendor, how you should create CSI Driver, and CSI means container storage interface, how driver should act so that Kubernetes can talk to it and tell it what user wanted to do. So if user create a PVC, like 5-seat car, and then storage class like SUV, or in this case, like bronze type storage class, CSI driver will actually go to a cloud storage backend, EBS. It will carve the volume based on storage class parameters. It will, and the size from PVC, then it will mount that volume to Kubernetes node. It will format it. It will mount to the container, and that's basically it. So this CSI driver is that invisible concierge which does all the dirty work that I have to do. So, and the provisioner in last slide is basically that name of CSI driver that is being used in the storage class. So every storage class needs to have CSI driver, this provisioner. So today there are like 200 CSI drivers for every storage vendor there is. And on for instance, AWS, there are 2 storage CSI drivers, one for EBS, block storage, and one for file system storage. But we're not going to use file system storage for databases. So that's how basically in a nutshell works storage provisioning in a Kubernetes for any stateful application. And CSI driver is not only useful during provisioning, like first few seconds of your database life, it's also useful for D2 operations. For instance, you run out of disk space. All you need to do is change in your PVC file size of the disk, and it will automatically resize the disk, re-extend the partition, and yeah, your database can write in that disk without any downtime or any changes that your database will notice. Also, some storage CSI drivers support advanced features like snapshotting and etc. So yeah, that quite a few of them. So demo, or it does not exist. So I'm going to quickly show you demo, how everything actually looks. So I have a Kubernetes cluster. I'm using, by the way, Lens client. It's really awesome for all of you who don't remember Kubernetes commands. Even though I'm certified Kubernetes administrator, I like this IDE for managing Kubernetes. So I have one Kubernetes node on Google Cloud. And if I go to, for instance, pods in a default namespace, let me go full screen, there's nothing, right? There's no application, anything in a default namespace. If I go to persisting volume claims in a default namespace, there's nothing. So, thing I want to create is, let me move that window here. Okay, so I have a Kubernetes object persisting volume claim to create a storage for payroll database, and it's going to be 9 gigabytes. So I'm creating a persisting volume claim, and here it is. So this persisting volume claim, I didn't specify storage class because I have default storage class. It's 9 gigabytes and it's pending. Why it's pending? So if I go to storage class and if I look at for instance, configuration of storage class, so it has wait for first consumer, meaning don't create storage until somebody comes and claims that storage, only then create it. Okay, so we have default storage. As you can see, it's a default true. So I'm going to close the storage. So I created PVC, which is kind of hanging. Nothing is using it. There's no actual disk created. It's just inside Kubernetes. So here I have simple MySQL database deployment. So database engine called payroll. It's like production. It's used by MyDB, image, MySQL, etc. Password, very secure for production. And interesting bits are here, mount points. So basically, I need to specify for container that there needs to be storage mounted on var lib_mysql directory, and the storage will be provided by payroll data volume. If I go to volumes, there's a payroll data volume, and it basically says there's a persisting volume claim called payroll data claim, which actually create the storage. So you can see in Kubernetes and in general in containers, runtime and persistence layers are decoupled. So you can manage like upgrade MySQL version, etc., without touching storage layer because it doesn't have anything even size defined. You manage those separately. So I'm gonna quickly deploy this MySQL container pod. So I see that container Kubernetes already created pod payroll, and I see that status has changed to bound. It means container asked for the storage and storage was created. So if I go to persistent volumes, I can see that there's a this volume created 19 seconds ago. That's the, let me copy the name. And yeah, it's used by this payroll data claim. So, and if I go here, I see my MySQL container running. For instance, if I go to Google Cloud and my Kubernetes is in Google Cloud, if I refresh disk, and I can quickly find it by ID, which I copied from Kubernetes, I see that physically in a Google Cloud, there was volume created in that availability zone on that node and attached to that node. Okay, so let's log into MySQL database. And MySQL, very secure unique password. And I have sample code just to create database, just simple table, insert data, and basically select from holidays, places. It basically database is working. So as you can see, it's quite easy to create a relational simple database on a Kubernetes. The challenges are actually in day-to problems when you have to do maintenance, etc. So I can show you a few more examples of CSI Driver. What it does, for instance, I'm running out of space in that database. So for instance, I can change from 9 gigabytes to like 14 gigabytes. I'm updating same persisting volume claim I created a few minutes ago. So I'm gonna submit it. And nice thing about Kubernetes that it is a declarative code. So you just specify what needs to happen. Like I want 14 gigabytes of volume, and I don't need to know how much there were before. It will synchronize the differences and make it happen. So as you can see, my persistent volume claim already shows 14 gigabytes of storage. If I go to persisting volume, it's already here, 14 gigs. If I go to database, like, and check in a, oh, I need to exit. Okay, so let me go again to, yeah, so I can see MySQL. We can see in MySQL that it's already 14 gigabytes volume extended and is there. So Alex, how are you on time? Do you have time for small little demo or?
Yeah, let's do a small demo.
Okay, so also as I mentioned, so as you can see, database was able to kind of on the fly, CSI Driver was able to on the fly extend the volume on running database, and my database is still running. And yeah, so for instance, you have production this database and you want to play around, you want have a copy of the data that you can use for development environment, and you don't want to actually fat finger production. And so what you can do is actually create a snapshot. So that's my original persistent volume claim name, and I'm saying I want to create a cloud storage snapshot from that persistent volume claim. So if I'm going to create that persistent volume claim, if I go to public cloud snapshots, I'm going to refresh. It will soon appear here in just a second. And so when I have a snapshot, and I can check if snapshot was created here. Yeah, snapshot is here. Snapshot contents, snapshot volume is here. And it's 14 kilobytes. Okay, it's not seeing. I'm not sure why I'm not seeing new volume, but let's maybe finish this demo prematurely. So
I think you created a snapshot for 12 gigs, to be honest.
Yeah, but snapshot doesn't need to specify how big it is.
Sorry.
So yeah, okay, that's probably okay. That may be an issue that I had a snapshot before. This demo I want to try running, and it's conflicting because I'm trying to create a duplicate. So if I give a new name, let's try again. If I'm going to refresh, yeah, we can see 14 gigs snapshot is being created. And so I can, let me see what's the created golden one. So I can create new persistent volume claim from a snapshot called snapshot golden. And for instance, I can create similar database MySQL as in production, just named like environment dev and development payroll. And if I'm going to create it here, if I go to pods, it's being created. So if I go to persistent volumes, so because snapshot hasn't been created yet, it takes, okay, snapshot is created. Let's wait a few seconds until persistent volume creates a volume from a snapshot. As you can see, it's created. And if we go to pod, so Kubernetes is saying, warning, your data, it's taking a bit too long for data to appear. So a few more seconds till container gets created. Okay, it's running. And if I open shell session to just development database, P for password, and show databases. As you can see, holidays here, so it allows to do a lot of cool things. Yeah, holiday places, or is it? Yeah. So that's end of my demo. So thank you very much for your time. And if you have any questions, I'm happy to answer them.
Yeah, please join the Slido channel and we can answer these questions. Okay, so let me name these questions. So the first one from Anonymous. Biggest problems while trying to run high-loaded databases. So that's left from previous one.
So I can answer that question here. So so CSI Driver is actually not in a data path of the storage. It's just an orchestrator. It helps you. It creates a volume and attaches volume, but you can remove CSI Driver. Your container is talking directly to storage backend. CSI Driver in itself doesn't have any performance penalty. What Alexei was referring probably is software-defined storage solutions that you can build on top of Kubernetes that runs on top of it, that adds performance penalty. So, and there's a lot of data proving that especially I/O in containers is no different from physical server. So you just need to give same amount CPU RAM and have a network throughput for storage, and you're going to have same performance as in physical server. So Kubernetes CSI driver is not in a path. They're just helping you as event organizer, but then you're going to live with that database storage like it was handled card by hand. So it's not really a performance question.
Okay, cool. Thanks for that one. Next one, how we go about database high availability when running on the Kubernetes? Too many loose parts.
So I think next session that Alexei is planning is about operators, and they are quite decent operators that do some backups for you. You create MySQL or Postgres in stateful set, where you have replication set for you. So they are trying to bring it. Some use it for production, but as Alexei said, it's not really what's created for it. I would just go directly with Yugabyte. They provide kind of SaaS, or they can install Kubernetes. They can install Yugabyte on your Kubernetes and manage for you. I think Cockroach can do that as well. It's not something you can get out of cloud provider directly, but there are partners who can help you manage modern distributed databases for you on Kubernetes, and they provide decent level consistency, same as Postgres. So.
Okay, cool. Thanks for that. Next question from Gitis. Is it so that bringing traditional databases to the cloud, like Kubernetes, main difficult is how database is used as a persistent storage, assuming it will not fail?
So, not sure I understand the question, but in Kubernetes, where, for instance, so I had my MySQL container with the storage. If, for instance, that physical server with that Kubernetes node would die with my MySQL container, if I had more nodes, that container would just appear on different node, and in a few seconds, like 30 seconds, I would have running MySQL server running with the same storage remapped to the new nodes. So I think storage CSI drivers are quite decent, and they kind of solve all these problems. So challenges with traditional databases are maintenance. So.
Okay, thanks. Okay, so next question is probably a similar one about how would you ensure needed I/O is delivered to databases. I think that's pretty much answered already, so we can skip it further. So Nereus, your database runs in Kubernetes, all is good until a pod is deployed to the same Kubernetes node as your database, and it starts consuming 100% CPU. Suddenly, rainy day for database.
So Kubernetes have very good resource scheduling mechanism. You specify request limits, how much your stuff can use it. There's a quality class for containers that define who gets more resources over other. If you actually start using CAS product, which helps you manage resources for you, we do that. So try CAS product, we can actually help that. But generally, silly error on users is that when they're creating container, they're not specifying how CPU and RAM request or network store throughput, etc. You can define what is non-negotiable, so no noisy neighbor can impact your database. And Kubernetes would kill those containers that are noisy going over their limit. They will be throttled down by CPU, or if they go with the memory, they will be killed with out of memory error. So Linux kernel does these things very well. They did it for 40 years, and that problem is solved. So.
Okay, cool. Thanks for that one. And currently the last one. I'm running Kubernetes on-prem, currently implemented with cluster and Hecate storage-wise. Anything I should be aware or any recommendations?
Actually, I'm not aware about Hecate storage-wise, so I'm not sure. So, but I think Thomas' presentation in just a minute kind of answers this software-defined storage question, because Gluster hits home here. So Thomas can answer that question, I think, better than me.
Okay, cool. Thanks, Agustinos. Okay,
Thank you for your time.
Yeah, we'll need to move further. Augustinus, one more time, thank you a lot. Probably you'll get a really good present from amazing stuff, some more amazing things. And let's move further. So yeah, so please welcome our next presenter. It's Thomas Raychunos, DevOps SRE engineering with experience working in financial institutions with private and public clouds. Engineer by day, do-it-yourself or by the night. Thomas will show you a practice example of juggling data on Kubernetes. So please welcome Thomas.
Hey guys, let me share my screen and let's get started. I hope you can see it fine.
Yep, all good.
Okay. So thanks, Augustinos and Alexei, for your presentations. That was really nice to hear. So I was the one that had the hard task of giving you a practical example on how to run database on Kubernetes. But as always, as you can hear or see, there is no single answer. So in my presentation, I will try to do a little twist. Let's focus on storage replication instead of running latest new SQL database available. So it's relatively easy to run database on Kubernetes. You just choose your flavor of cloud distributed database like Cockroach, Yugabyte, NuoDB, TipDB, Vitesse, and call it a day, right? However, I'll try to show you another approach on focusing not on database engine, but on storage instead. In essential storage, the data is replicated across multiple availability zones. When it's possible to start another instance of your database on copy of your data and have easy fault tolerance set up that way. Basically, what I'm saying is you can always do your data replication in the background to run another availability zone. So in this case, you need to rely on storage or a middle storage layer that could do the replication for you. So be it Ceph, OpenEBS, Longhorn, GlusterFS, or Portworx. I'll be using Portworx for this demonstration because of personal preference, but as I mentioned, it can be done with any other tool. So here's a simple diagram of cluster spanning 3 availability zones. Let's say I have a pod that uses persistent storage and is running on AZ2. Since native persistent storage is availability zone bound, meaning you cannot schedule the pod on another availability zone and make him use data on another one. So using middle storage layer for persistent volume can synchronously replicate, and in case of AZ failure, it can shift pod for you where that copy exists already. So moving pod from AZ2 to AZ1, where the copy exists already. I'll show this in the demo later. Of course, don't forget to use the questions in our Slido. So things to consider before doing that. Storage replication is not free. It adds latency to your application response, where it needs to wait for data to be written on multiple disks on other availability zones. So middle storage layer can ensure strong consistency. Overall, rule of thumb, like total latency equals network latency between availability zones times replica count. Cluster topology is also important. So it's better that nodes are closer, like network-wise, they are closer together. And yeah, of course, don't put all your nodes in one availability zone. It's stupid. Same goes for regional replication. If latency is not too bad, generally less than 10 milliseconds, it's possible to have storage sync between regions as well. If latency is bigger than that, then you need to do a synchronous replication, but it's another can of worms and subject for another day. So to sum up, adding the middle layer, it's slower, more expensive, but more resilient. So would you even consider running this storage replication on distributed databases like the new SQL ones? In short, lifting and placing pod on node where second replica already exists improves the recovery time, because otherwise your application node needs to make a new node and make a copy of existing data from another application nodes. And that can take some time, especially if you have a big data set. So result, basically, you can decrease recovery time and improve application performance, because your application on replicated data can perform almost 100% and almost instantly. So for demo, as I said, I'll be using Portworx and Minaya. Before you start shouting, of course, yes, I'm aware Minaya is not a database. I chose it because of ease of use for demo purposes. Just think of it as object database. So if you're not familiar with Minaya, it's a highly performance object storage like AWS S3. Where it's running in distributed mode, it ensures that data is replicated on multiple drives, tolerating half of servers loss. And Portworx is a proprietary product. Basically, it's a cluster block storage solution that provides a cloud-native storage layer abstraction. So for demo, let's see what happens when regular GKE is set up. And then, let's see how regular GKE setup performs. And then let's introduce a middle layer in another demo. In case of failure, only pod is moved from one AZ to another, and the data will be already present and waiting for that pod. This result result is that your pod will spin up in a few seconds, and you won't have any data loss in case of AZ2 failure. So let's hope demo hods are in a good mood today and everything will go well. Also, don't be frightened unless, like Augustinas, I'm using K9S, which is a bit different interface. But once you learn a few shortcuts, you don't need to touch mouse ever again. So let's start. Here I have a cluster of 6 nodes spanning 3 availability zones, so 2 nodes per zone. Let's jump to namespace where I have Minaya running. So basically, this is the example how you should never, ever run your setup. This is a Minaya pod. It's using PVC claim, which is using standard storage class that Kubernetes and GKE provide. We can have a look at the interface. So basically, this is my object, just any object. And we can see it's running. I can add or remove data from it. Now, let's get back to this. I see that my pod is running on this node, SF26. So let's cordon all nodes on same availability zone. So availability zone number 2 is like dead to that pod. And let's kill it. It's dead, it's pending, and it will keep on pending because there is no way Kubernetes can run that pod on zone where it doesn't have the data. If we look at the interface, boom, you lost your service. Let's go to the example where we can have a look on how to run single pod with data replication. So again, same setup, but the main difference is that I'm using PVC, which has another storage class, min.io.sc, and this time the provisioner is Portworx. If we have a look at that storage class, the main parameters we are interested in are these. IO profile CMS is basically the caching algorithm that Portworx use. And REPL2, basically here you define the amount of replicas that middle layer ensures that are always going to be present and spread across different availability zones. So in our case, it's 2. Let's jump on our interface. Same setup, single object. So my pod is running on node ending in MCXX. It's already cordoned, so it's easy to. And let's kill this pod. And this type, unlike other, you can see that the pod is restarting and starting to run. And if you have a look, you see that it's running on another node. And if you look, sorry. If you look, that node is in another availability zone. So West 1D, instead of cordoned one that was West 1C. If we check the interface, we can see that everything is running. We can add new objects. All is good. Yay. So let's check if we can do the same thing with distributed database or distributed min.io set. Jump to the namespace. Yeah. Here you can see that I'm running 4 pods, and those pods are doing data replication on the application level as well. I'm using same example as in the first one. So PVCs are the default ones. We're using standard storage class, and we're using Kubernetes provisioner using GKE. So let's choose some pods to kill. 7ZKs. Let's cordon these ones. Oh yeah. And let me show you that the application is really running. Sorry, it's from old example. Yeah, it's running, it's fine. And let's try to kill this and this guy. Boom. So again, as we see as we saw it in the first example, nodes won't be able to be rescheduled on our availability zone. It'll be just keep on pending. But hey, we had a cluster like out of 4. Now we have 2 left. Yes, we have 2 left. And our min.io is kind of running. As you can see, it's slower, but it should spit out an object I had before. Yay. But basically, because we lost half of our cluster, we are not able to do writes anymore. So if I try to add something else, it will just keep on retrying and fail until those nodes or the availability zone is back online. So basically, I have a cluster that's kind of working, but it has degraded performance. Okay. Last example, same setup, but only running distributed mode with replication. Let's see. With replication. Check, yes. KNX node is cordoned. Let's do the same thing and let's kick these pods. So unlike in the last example, we see that pods are starting. We've been scheduled to another availability zone. Let's check our interface. Again, because nodes will be scheduled, it will take some time for Minio to do shards reindexing. But as we can see, it's up and running, and I can add data to it. Yay. Cool. So hope this gives you like a brief overview of other possibilities, not just using the latest and the greatest databases that are available, but not really tested yet. Cool. So that's it from me. Any questions?
Thanks, Thomas. Thanks, that was really good. Let's go to some questions. Okay, the first one from the Anonymous. If you're running 5 MySQL min.io pods, stateful set cluster, is it possible to bound them to one volume claim, or how does this work from storage perspective?
Each pod, if you're running it in stateful set, each of them has its own PVC or stateful set, persistent volume claim. I hope I got the answer right.
Yeah, so basically it's a separate disks for each
Yeah.
Cool, thanks. Do you aware about database challenges that comes into the GEO distributed Kubernetes clusters? Workers in different regions.
Personally, no, we haven't tackled this yet, but probably having stretch, I guess it depends on your locations. If your regions are close together, then it's fine. If not, you can have some unexpected latency bumps that would affect your application. So that wouldn't be good. So if possible, I guess the good solution would be to mitigate this and don't have cluster stretch across availability zones. But I guess Augustinas could second to that better.
Okay, cool. So not a lot of black magic around it.
Yeah, basically use it with caution.
Yep. How about replication between regions instead of zones? What are additional challenges? I think it's pretty much same as.
As I mentioned, the biggest enemy here is latency because it adds to overall application response. If you manage to have your network latency as low as possible, that will help you. If not, you need to take this into consideration or find other workarounds like doing asynchronous replication.
Yeah, okay, thanks. For the backup, should we utilize volume snapshot or should we create our own mechanism to store database backup on AWS S3 EFS?
If you're not afraid of tying into the cloud provider, then you can use Csi Driver to do the snapshots as Augustina showed. If not, you could do regular database backup to, let's say, min.io cluster running on your Kubernetes, or you can use a solution like Portworx, which does basically EBS block storage snapshots and rely on the middle layer as well. So like at least three options here.
Okay, thanks. So it's either block storage or database ones.
Yeah.
Okay, cool. Seems no more questions. Thanks a lot, Thomas, for this great presentation. And you also should get a small present from Amazing Stuff soon, so bear with us. Thanks a lot. Also, thanks a lot for all other participants. I think we are moving towards the end of our meetup here. Please track us on the social medias like Facebook, LinkedIn for upcoming events, since we will be talking more in details about the database operator. What do they do? How do they help? We'll talk about concrete database like MySQL and Kubernetes with all the necessary demo out there. Also, I wanted to thank our main sponsors who are Mambu and Cast.ai for making this webinar happen and all of the series of them. So thanks you guys out there. Also, please bear with us. We value your feedback, and don't forget to fill out the feedback form if you would like to participate in next events, if you would like to know more about the amazing stuff, if you would like to join our channels, join our community, please do that one through the feedback form or directly to myself. You can find me on Slack channel. Always I'm there, so please bear with us. Also, if you have any other questions around our sponsors, Mambo and Cast.ai, you could reach me out directly or through the feedback form there. So thank you all and have a good day. Stay healthy and see you soon.